this measures how player 3 would be in a better position than player 1 and player 2. And this measures how that coalition data would be. So the model has that, well, again, the nucleolus says that they all equally should get equally, even though there's some coalition difference, except when this becomes 1/3, when these become, and then they can get more. In fact, then it moves up very rapidly. And in the end, if the coalitions reach a maximal level, coalition either player 1 and player 3, or player 2 and player 3 can get all of the payoff, then it becomes a model type of game that's called the gloves game. It's analogous to a situation where there's 3 people have gloves, but there's 1 right-handed glove and 2 left-handed gloves. And player 3 would be the one with the right-handed glove. Well, so if this goes up to 1, the nucleolus differs from the Shapley value. The nucleolus says that player 3 then gets everything. But the Shapley value says something different, that he gets most all of it, but not all. And but the model is giving a very slight, where it can be calculated. It doesn't go all the way to 0.7, but the actual computed results had that player 3 was not getting so much of a benefit. So you get different indications. Now, I don't know how much time I should take, but some experiments were related to these calculations, the model calculation, and also the general idea that you could have cooperation formed by an acceptance process. This can be tested experimentally. I don't know if I should go on, but some experiments were done actually in Cologne in the laboratory of Axel Ockenfels, who's economics and game theory in University of Cologne. And the experiments were designed. I was involved. Reinhard Zelten, who's very interested in experiments in these days, he shared with me in the trip to Stockholm in 1994. And the other one was John Harsanyi, who died a few years ago, who was older. He was the oldest. But I have this, I think it's somewhere else. This I have I was giving a lecture based on some calculations with the experimental idea. There was an experiment where players were allowed to just accept other players and the acceptance process and do it on a repeated basis. But the behavior, you could say, was not entirely, it wasn't clear that behavior had exactly stabilized to a pattern. And they did sometimes some simple-minded things. This is a group. Those are the cooperating things. That UPF is a university in Barcelona, and I forget LEX. Because Zelten is retired, but he's emeritus in Bonn. Oh, well, this is the first page. Now, these results, there's some studies and experiments, and then the experiments, if you add up, if you have a particular model game that's designed in the form that is designed for the experiment, players are using acceptance processes in order to cooperate. And there are rules that it's not the demand, it's not the mathematics, it's not the equilibrium calculations that I was doing, but it relates to the sort of the social situation. So here's some things. Now, Zeldin had some ideas of payoff bounds, and other persons have had bounds ideas of that sort. So they made some comparisons. It turned out that my actual model calculation could only work on one of the 10 experimental games because they had the correlation strengths were too strong. My thing would work out well if the two-player correlations were all comparatively weak. Or not too strong. But these turned out now this is my other stuff. This is a reference. This is a reference to the previous study which you have seen. Wait a minute. I think that is page down. It doesn't work. Well, here's the actual modeling. If I went into this was sort of where it worked out. This flowchart was actually done by Professor Zeldin. And it's the basic idea, but he has formulated it very logically, and the terminology is somewhat changed. See, there's an eligible pair concept. It's a different term. An eligible pair is where one player has been accepted as the accepted agent by some other player. Well, there were only 10 games of this sort, and these numbers would compare with the numbers I was calling B1, B2, and B3, but this is not normalized to the total is 1, rather the total is 120. You see that up there. There's some examples where the correlation of 1 and 2 is so strong it could take everything. In fact, the first 4 are like that. And then, now, my model worked only for this one as the present form of it. That if the correlations, if these were not too strong, this one I could actually get the model to work and produce numbers, or approximate numbers. And I've been working a long time on the game 9, which is a little different, but it would seem that in the game 9, according to my model, some of the optional behavior quantities should be 0. So then that changes the equation. And I'm getting, my method of computing is very slowly converging. And I think this suggests a problem in itself, that a good area of study is how to find solutions of simultaneous equations when a simple iterative method is slowly converging. This is a mathematical problem. There's a special art in solving simultaneous equations. It's not something that has been done really systematically in mathematics. If there are linear equations, it's all known. But it's not linear. Now, these are some statistics. Actual average payoffs. Now, the efficiency over here is what could be called by an economist the Pareto efficiency. But the possibility is of 1, but if they're getting like 95%, and in the first games, actually, you have complete efficiency if player 1 and player 2